Thanks so much for being here on a Saturday morning. Thanks so much for the organizers for inviting me. Thanks so much for Jacob for writing such a nice paper. I teach MBAs in this exact room, so there's a nice change of pace from my normal Monday in life. And now I get to talk about weak overlap. So what the paper is it's about a situation where you want to do inference in a situation where treatment is as good as randomly assigned after you controlled for a set of covariates. So in an experiment, it could be that you stratified and you said, okay, for people in this age, sex, whatever bin, I'm going to randomly assign treatment. So once you control for these, treatment is as good as randomly assigned. That treatment assignment probability may vary with the bin, so that's fine. The other situation where this is good for is, well, you might say I have observational data, and after controlling for this, a patient presents in a certain way. So a patient with, this set of observable characteristics, a doctor could go one way or the other, so they could choose to do an intervention or not, but these are the covariates that matter in a situation like this. Now what happens is you might be in a situation where if you look at your covariate bin, in which treatment is supposed to be as good as randomly assigned, you might be in a situation where the assignment probabilities are such that it is very likely or very unlikely that somebody receives treatment. So you might have chosen in your experiment after stratifying on certain characteristics, you might have decided to overtreat or undertreat for whatever reason, or you might be in a situation where, okay, with certain characteristics, many physicians agree that this intervention should be done, or many physicians agree that it shouldn't be done. So you might be in a situation where very few or very many people receive treatment. And this is a situation that's called weak overlap or limited overlap. And what that really means is, in order to back out that effect, we're going to see that later, in order to back out the effect of that intervention, we have to scale up that effect by the probability of treatment. And the scaling up means we're dividing by a probability, and if that probability is really close to zero, or 1 minus that probability is really close to zero, it's not surprising that things become very unstable. And unstable manifests itself in, well, at first it manifests itself in that, your variances start to increase, but the problem is actually much more grave. And there's a famous paper by Kahn and Tamer that quantifies that in a quite shocking manner. Things become near impossible. So they characterize quite precisely that as soon as we are outside of this world where, well, we have a nice balance of treated and control units in these covariate bins, once we're sort of lopsided, things kind of go out the door. So behavior of estimators that you would sort of expect now starts to disappear. Convergence of estimators becomes much more slow, and eventually things go really wrong. So eventually things, become impossible or near impossible. Which again, in a way it's not surprising. If you divide something by zero, bad things happen, but they characterize that quite precisely. And one quite subtle consequence of their results, I think people originally looked at them and were like, okay, yes, convergence real bad, right? But one interesting and I think relatively subtle consequence that wasn't realized right away was, well, if our task was to say, look, I want to estimate average treatment effects, and then I want to do a nice confidence interval where I just say, okay, I'm taking my point estimate, and now I center my confidence interval at the point estimate, and I go plus minus, a normal critical value times a standard error, that is now a confidence interval, maybe depending on, in a relatively broad class of models, this may be impossible. And so standard inference, the way you kind of want it to do, can go out the door. And what I mean by going out the door is you're trying to do a 5% level test in a sense that you want to accidentally discover an effect even though there is none in 5% of all cases. And I'm making up these numbers, but I can generate them for you. You would discover a non-existent effect in 60% of all cases. So you would find complete bogus for no reason at all. Now, what Jacob does is he shows actually if we put a teeny tiny little bit more structure on the problem, this thing that Kahn and Tamis say is impossible actually becomes quite possible. He can give us a very standard estimator and then centered, like a confidence interval centered at that estimator where plus minus normal critical value times standard error, all of a sudden that is a very normal, very reasonable confidence interval where, look, you want to run a 5% level test and this is a 95%, coverage probability for that confidence interval. The way Jacob does that is very clever. So a lot of the literature has focused on, trying to take an estimator and then debias it or modify it in a certain way. And Jacob points out that if we use a very standard estimator, the doubly robust IPW estimator, that thing already has some debiasing built in. So if we do a slight adjustment to that estimator where we snip off in a clever way treatment probabilities, propensity scores, if we snip those off in a clever way, we can make this work. We can return to standard, confidence intervals. All these sort of things that we might have thought were impossible, all of a sudden become quite possible. And for that, and this undersells the paper, I just want to point out, but for that, things have to be just right. And Jacob tells us very precisely how right they have to be. So if we don't snip off, if we don't threshold those propensity scores enough, we're in this world of Kahn and Tamer where things go really poorly. If we snip off too much, we're in a situation where okay, now if I snip off that propensity score, I'm sort of changing what the data tells us about treatment assignment probabilities. So that in a way changes what we are estimating. So all of a sudden you might be targeting a very different population. What you're estimating might change. So you have to do that in just the right way. Jacob characterizes that very precisely in the paper. I think the key technical contribution here in Jacob's paper is that he gives us very precisely the situation under which, the snipping off of these, problematic propensity scores is just right, and he tells us very precisely how to do it, under which conditions, and he gives clear guidance for empirical practice on how this should be done. Now, let me very briefly, in case you're not a super technical person, let me very briefly tell you, quickly what all of this actually means if, propensity scores and whatnot is not something you've come across. So, again, we are in a world where I'm saying conditional on a certain set of covariates, treatment is as good as randomly assigned, or, in words, like in technical words, this is, well, treatment and my potential outcomes, treated and control potential outcomes, are independent conditional on these covariates. And I think the applied person in me, at that point when I see something like that, I'm kind of like, look, that's not so bad. I have a good idea. How about we run a regression? And so you generate yourself your observed outcome, which depends on whether you receive treatment or not. And so why don't you then just run a regression? So you could run a regression that's, outcome on treatment, constant treatment indicator, and then maybe a very flexible function that accounts for all these covariates. You might have a really good idea what these covariates are and what they look like. And I have to tell you, even then, if your treatment effects are not constant, even then, this is a really bad regression, unfortunately. So if the so I'm looking at this thing here. So if the treatment effect is not the same for everyone, so let's say there's some intervention and Jacob's treatment effect is 2, but Edwards is 22, right? Then on average they have a treatment effect. We have a treatment effect of 12. And Constant would say, well, everyone has a treatment effect of 12. So if we're not in this situation, then running this regression is a really, really bad idea. And the reason why it is, well, if you look at the error term here, if you look at what type of assumptions would need to be in place for this to work, you wouldn't want to do it. So just running a regression here is, like, even though it looks inviting, is a bad idea. It does not recover average treatment effects under reasonable assumptions. So even if you kind of feel like I'm running this regression and, regression somehow averages things out, this beta 1 is somehow going to be some average that I can work with. It is unfortunately not. So you run this with a non-constant treatment effect. Your beta 1 is generally not something that is reasonable, interpretable, whatnot. So what do you do instead? You instead do IPW, inverse probability weighting, which is what Jacob does. Now, inverse probability weighting, IPW or AIPW, augmented inverse probability weighting, recovers average treatment effects just fine as long as you have this thing called overlap, and overlap just says if the propensity score E of X, which is the probability of treatment given covariance, if that is between 0 and 1, meaning that I have both people in the treated group and I have people in the control group for these bins, then it's not surprising that I can estimate things. So I have a propensity score. I'm interested in estimating the average effect of treatment. Now, if I'm interested in the average effect of treatment, I'm essentially interested in the expectation of Y1 and I'm interested in the expectation of Y naught. So I'm going to focus on the expectation of Y1, and you could do the expectation of Y naught as a homework exercise. So my expectation of Y1, so my expectation of the treated potential outcome, if you squint under my conditional independence assumption, this independence assumption that I made, and my limited overlap, my overlap assumption, you can kind of squint and then see that, not working today, you can kind of squint and see that, this thing here on the left-hand side is identified as the thing here on the right-hand side. How exactly doesn't really matter for what we're doing here today. Dividing by the propensity score, however, is important because you see if you divide it here by 0, identification goes out the door. The sample version of this is we're estimating this propensity score as a flexible function. These are my treatment indicators, these are my outcomes. Everything should go through just fine. You might be familiar with a sort of fancier version of this exact estimate. That's the doubly robust or augmented version of this estimator. And what it does, it takes the, it takes the regular estimator and it subtracts a little something. And again, I'm not going to go into the details of that little something that I'm subtracting here, but what it does, and again, you might be completely familiar with this or you might be not, but what it does, there's sort of a slight biasing that happens here that helps you in case your propensity score is not that well estimated. There's a second thing that comes in, and that's an estimate of this expectation, the expectation of the outcome in the treated group given certain covariates. That's again, you would use a non-parametric, a very flexible estimate for this. And the motivation for the doubly robust estimate is essentially, look, if our estimate of that propensity score, if that's a little wobbly, this thing over here comes in and essentially substitutes in this object here, which when one or the other, either the E hat or the U hat, if one of those is well estimated, that's enough for this estimate to do good things. So this entire object here really just helps out a little bit in case this estimator up here, the IPW estimator, is a little bit wobbly. Now again, it's not surprising that if I were to do something like this, but my E of X, my propensity score, my probability of treatment given being in certain covariate bins, if that is small and I'm dividing by that, if I'm near zero, then that's a pretty bad time. So if I'm doing that here, well, there's many ways that I can try and fix that. One way is me saying, well, if my propensity score that I'm getting, if that one's real small, I'm just gonna clip it off and I'm gonna replace it by this quantity Bn, just kind of like a bandwidth or a threshold where we're saying if we're below this threshold Bn, I'm gonna replace a really small quantity by Bn. And what that does, right, is sort of regularizes the estimate where we're saying, okay, we're throwing out stuff near zero and, we're replacing it by something that provides a bit of stability to that estimate. And, then it makes sense that, if you think about it, if we have Bn sort of at a decent level, not too big, not too small, that's still, the theory behind this becomes very involved. A couple of years ago, we had a couple very smart PhD students here at Michigan. Shinwei Ma, who maybe some of you guys remember here as a very bright student in the econ department, or Ying-Shen Wan, a very bright student in the stats department. They wrote a paper together while they were here in JASA. Shinwei just got tenure at UC San Diego. Ying-Shen is still moving through the system at Berkeley, and she is crushing it. They wrote a paper in JASA, and they say, look, suppose we're putting a little bit of structure on what these tails can look like. So suppose we're looking at the distribution of the propensity score and think about, well, what makes it so bad, right? The problem is really, really small propensity scores. So suppose we put a little bit of structure on the distribution of these propensity scores if they are near zero. So do they linger near zero, or is it just quite unlikely that they are near zero? And so they put a little bit of structure on there. They put essentially bounds on there that say, look, this cannot be much worse than a polynomial. And if it's a small polynomial, then things go really south, we're in the Kahn-Thema situation. If it's a big polynomial or near exponential, then we're sort of in this normal situation where things go really well. So they sort of find the exact lever that tells us here's where things go wrong, here's where things go right. And they show, look, kind of the lower this, polynomial is, the more this takes us away from the domain of attraction of the normal law and takes us into the domain of attraction of some really scary, unfortunate distributions. So they characterize that quite precisely. Much of their papers about, characterizing this, and I still remember they ran into terrible issues trying to get the inference worked out, because the problem that happens is, look, you clip things a little bit. If you clip too much, right, you really change the propensity score. You really change, right? Instead of saying like, oh, it's 0.05, you're saying, oh, I'm clipping it to be BN, so I'm clipping it to be 0.1. So you're really changing what you're estimating. So what they have to do is they have to clip, but they have to make that clipping go away very slowly. And this very slow clipping causes a lot of bias. So they get bias in their estimates, and then they have to do a second step where essentially have to remove that bias again in order to get out of this, which leads to, very complicated inference. They have to do subsampling essentially because subsampling is really good at adapting to this gamma parameter without knowing that gamma parameter sort of as things slide around. This gamma parameter changes sort of from a normal distribution, changes things from a normal distribution to really quite complicated distributions, and subsampling does that quite well. But so you're in a situation where like this works great, but the inference is quite unfortunate. Now, what Jacob tells us is, don't worry so much about the inference. We can fix that, or he can fix that. And instead of just running IPW, he says, suppose you have a, suppose instead of just running IPW, use the doubly robust estimate, because the doubly robust estimate already has some bias reduction built in, so why not use that bias reduction? So he also clips a little bit, but he just clips, the regular estimate, and then he also clips, the bias reduction. So it's just the doubly robust IPW estimator, slightly clipped. We're still, like in that second term, there's still that flexible estimate that you have that helps you with that bias reduction. But again, it's that second term that helps you, remove essentially bias from estimating that propensity score quite poorly. Again, we are again in a situation where if we clip this thing off, again, in a sense, we're changing what we are estimating. So we have to be very careful about clipping things off. And the question that Jacob sets out is like, can we make it such that this doesn't matter? Can we clip in such a way such that this works? And Jacob points out a very important thing, again, and I'm underselling this point, is a very delicate argument. And it's not just sort of this very standard like bandwidth argument where it's like, yes, the bandwidth has to be right because otherwise it will be wrong. It's a very delicate argument where it shows, look, if we're clipping too much, or if we have to clip quite a bit in order to get back to standard normal inference, but because of that, we're generating bias, and we don't want that bias. We need that bias to be relatively small. So we need to be between this restoring normality and this, I can't have all that bias from clipping in there. So we need to be in a very specific region of this clipping nuisance parameter in order to get something that is just right. And with that, we are at Jacob's main result. We take the doubly robust estimate, and then Jacob tells us the following thing. Suppose we have a propensity score that behaves reasonable. Reasonable here means it's nice and smooth. Suppose we have, this outcome regression is outcome mean parameter. That's also nice and smooth. Overlap can be weak. It doesn't matter. It obviously cannot be too weak if you're always dividing by 0. What are you going to do, right? So it can be weak. In that case, that's all you're really assuming. Jacob can give us local polynomials, very specific estimators of the propensity score and this mean object, and he gives us a clipping rate, and that clipping rate, again, he very precisely characterizes. That clipping rate depends on how smooth the propensity score and that mean function is, but when you're estimating the propensity score and the mean function, you're gonna make smoothness assumptions anyway, so Jacob really only says, you might as well use those right here, right? So essentially under assumptions where you say, I would estimate these, he's saying, well, under the same-ish assumptions, I can give you a clipping rate such that this doubly robust estimator, this up here, has a nice normal limiting distribution with a critical value and a standard error that he also gives you. It's just a normal critical value and a standard error that he can estimate. And that's a confidence interval that covers in a large sample with 95% probability. The formal statement of this is tricky. One nice feature of this formal statement, however, is that this clipping rate doesn't depend on these like pi and gamma parameters that I just showed you guys. It's really only the smoothness that matters here. And if you look at his simulations, you see exactly what's going on in action. So what we have here in the top of this panel, here we have the IPW estimator. So that's before Jacob does the double robust thing. So we use the regular IPW estimator. The blue line is essentially what we would like it to be. The blue line is just sort of the right normal distribution. And you see the IPW estimator, the location is sort of shifted to the left. That's the bias that manifests itself. And in the bottom, we see, well, that's Jacob's doubly robust or augmented IPW estimator. We see exactly, this now shifts it in the right location. So this is why Jacob's thing works. It's the automatic bias correction that is built into the estimator is enough to get us back to standard normal inference. Up here, right, standard normal inference would be wrong. We would be in the top panel, we would be in a situation because the location is wrong, we would discover effects that are not even there. I'm supposed to comment on this, so let me give a couple comments. In terms of, if I were a referee, what would I be concerned with? Now, in a situation like this, right, you have to make some assumptions. And Jacob makes some very reasonable assumptions in order to get somewhere. So what he essentially assumes is that those two functions that we're estimating non-parametrically, they gotta be real quite good. So you cannot be too wrong in those estimates. You gotta be quite confident that those estimates are good. So there isn't that much of a sort of robustness thing going on in this AIPW estimator anymore, where you can have some leeway of this going wrong. These have to be really quite right. And you rely on the researcher making good guesses about the smoothness of these two functions that we're estimating. So you have to make good guesses about this. You have to make good guesses about the tail behavior. And with that, you sort of imply that you're also making a good guess about the clipping rate. So there's a lot of things that have to go right here in order for us to say something reasonable. The other thing that I kind of swept under the rug early on was I'm only looking at the expectation of the treated potential outcome. If we're looking at the control potential outcome, right, we could be in a situation where, right, as I said, well, if physicians all agree or mostly agree that everybody should, or almost everybody should receive treatment, then you might have a propensity score near 1, but you might not have a propensity score that's near 0. So it's not clear that the same assumptions that we made for Y1 also need to apply to Y naught. So if that's the case, well, we're not only making sort of assumptions about 2 functions and a clipping parameter and another thing, we're making, you know, twice that. So instead of making 5 assumptions, we're not making 10 assumptions, and we have to be comfortable with that. The other thing, and that's sort of like the bootstrap person in me, but if I see weights, I'd like those weights to sum up to 1. So my question to Jacob would be, would it be any better if I made it so that the weights, and because IPW is weighting, but the weights of the IPW, especially the one that he produces, don't add up to 1. We could just make them add up to 1. Would this stabilize? My other 2 comments are not specific to Jacob's paper, more generally about the literature. But my beef with, I don't know, I'm going over time, but give me 1 minute, okay? My 1 minute rant about weak overlap is, so if we are in a situation where all the physicians agree that this person should get treatment, then what the heck is my control group, right? Those are probably really weird people. This might be like folks who are like with religious exceptions. They're probably different on a variety of other dimensions too that we do not observe. So what are we doing using folks of which we have almost nobody and very little information about them? What are we doing if in observational data where we just know nothing and everybody agrees that this person should get surgery, but they don't, they choose not to? What are we saying, like, you know, being like, oh, this is as good as randomly assigned? So I think, in general, I think weak overlap here it's a tricky thing to, I think, defend in a lot of observational data in the same way as much of selection of unobservables is tricky to defend in much of observational data. The other thing, and that's because I'm a small sample guy, but if we are, like, this paper and every other paper essentially is almost every other paper is, well, we're showing a large sample solution to something that's a small sample problem. What we have here is what Christoph wrote in a 2017 Econometrica called locally small samples, right? The problem really is, as my sample size grows very large, my control group or my treatment group are tiny, 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 and I'm comparing a large sample to a very small sample, and you know, essentially the asymptotic promise is like, yes, but as the sample grows really big, that sample will eventually grow large. So it seems like a large sample solution to a small sample problem might have the idea. Okay, let me stop here. There's a wonderful paper, super strong theoretical results. I love that it's not just a theory paper. Everything that Jacob does is getting us towards empirical practice, doing something right in empirical practice. He has a very clear way of saying, this is how you should do it. You gotta, you know, this is how you estimate, this is your bandwidth, this is what you're doing. It's not just some like, and then there's a bandwidth. So you can run this estimator right now today. There isn't some special secret sauce, and you can tell Jacob worked hard on making this relevant for people. Other than that, I just want to say this was an absolute pleasure to read. Jacob's fantastic writer. You should read it too. Thanks so much.
If I speak like this, can folks hear okay? Okay, awesome. So a few notes. Thank you, Andreas, for the very, very kind discussion. I know this paper was, I think, a fair lift, and so I really appreciate the time. Also, just generally, thank you to the organizers for organizing this. My main work's actually in Health I/O, but I do some, econometrics. So it's, this conference is a real treat to kind of see all these people who I look up to and I love their work from different worlds. Yeah, I should say it was a bit of an awkward fit, I thought, but then it did occur to me that Ma and Wong's a super foundational paper that I'm building on, and it was really, really great to have this discussed by someone who was, there when the paper started. Okay, so a few notes mostly are just kind of agreeing, maybe with a twist. So one is the setup. I think it was a really important nuance that the paper is currently missing. That sort of, if we're in a world where we really believe in constant treatment effects, then weak overlap really isn't much of an issue, because you can just ignore the hard population and we learn the treatment effect in the easy population and we can extrapolate. Right? Really where it is we need this is the case where we think that the treatment effects are different in this area where there's weak overlap. And so if we want to know about the population as a whole, we really need to do something to figure out what's going on there. And if we critique, maybe we shouldn't care about that population as a whole, and I am completely on board with we should be unpacking our average treatment effects. But right now I think we write a lot of papers that really are just, is this treatment good, is this treatment bad? And if we're saying this treatment is good, then we should be careful. Is it that it actually is good, or is it that it's good in the population that sometimes gets it, but then there's this population that doctors know shouldn't be getting it, and if we throw them out, we're going to miss the bad outcomes and just say it's good. Okay, a few other things. One subtle note that I think I need to do a better job of explaining. So it wasn't actually clear to me before I started this paper, but actually the threshold not being too small, it's actually not the normality that's the issue. It turns out that if you're snipping at a rate that goes to 0 slower than 10 to the -1/2, Berry-Yassine theorem will say we get asymptotic normality. It actually turns out that the problem is still bias. Right, so Andreas emphasized well that if we throw out too much data, we're going to introduce bias. But also we're dividing by this threshold Bn, meaning if Bn is too small, even if we have asymptotic normality, we're still dividing by a lot of small numbers, and that is again going to make it really easy to get bias from getting the propensity score wrong. So in the Ma and Wong framework, we know the propensity score, and so that's not an issue. But here actually it's really bias versus bias that we need to control. But otherwise completely on board. Thought I had 6. Yes. Okay. Really good point that a subtlety I hadn't appreciated, the symmetry. So I do the analysis focusing on the expected treatment potential outcome, even though we really care about the treatment effect. Basically, it's just going to cut the notation by 50%, and that's nice. But what that led me to miss when I was running this paper, this is a really good point, so obviously we're going to have separate assumptions, but really what we need is the bias to be smaller than the standard error, because we're doing this debiasing thing, and the biases might be different, but if we're interested in the ATE, the standard error is the same. And so that means that right now I'm saying, let's decouple and choose thresholds separately, but there's probably some power to be gained by thinking about them at the same time, and there'll be a better rule of thumb for it. And then a couple simulation-related notes. So one, this point about small sample, I think is a really good one. So I don't think the p-values are on these slides. My favorite graph is actually not the t-statistics, it's the p-values. So because we want to have uniform p-values, what you see is if you have 1,000 observations in the simulations, right, we over-reject, I think, by a factor of like 50%. We reject something like 7.5% of the time. In large samples, we reject something like 5.3, 5.4% of the time, and a Kolmogorov-Smirnov test can't reject that the p-values are uniform, meaning we see the asymptotic result that we get exact coverage, but the point is very well taken that in small samples, the bias might be meaningful enough to over-reject by a bit. I don't have a solution, but I agree it's a problem, a challenge. I don't know there's something better yet, but hopefully someone can come up with it. And then this question of what happens if we stabilize, if we don't just take the the average of the propensities, but we divide by their average and not just the number, n or 1. And so what's the idea? The idea here is that if we have a bunch of treated observations with small estimated propensity scores, we have, if they have not many, if we have small weight, we're kind of okay. What's really a problem is when we have a lot of, observations that we estimate E of x too small, and so we divide by too many big numbers and we get too much weight. That really causes some issues, and so the stabilizing might be able to help. So I have some simulations where I did this. I didn't think anyone would care, so I didn't really mention them in the paper. Right, I focus thinking about two cases. So one is this clipping where you windsorize. One is trimming where you say if the propensity score is below Bn, we pretend you weren't treated. If you trim, you kind of throw out more big weights. You get a larger standard error. You get a smaller standard error, a larger bias. As a result, you get more over rejection. It turns out the stabilizing kind of gets you a standard error that's really close to trimming, because you're again avoiding this issue of having a bunch of large weights. But it has less bias because you're still doing something in these regions below the n, and that gets you close to clipping. You get a little bit more bias, and as a result, you get a little bit more over rejection. So in the simulations, when you go to 100,000 observations, clipping rejects 5.5% of the time or something. If you stabilize, you reject like 5.9% of the time, which is enough for Kolmogorov-Smirnov to say, you're not quite uniform. But that might be worth it for, better standard errors. So those are the things that I wanted to mention. And, yeah, happy to open up to questions. Yeah.
First, as a blind person, it's great to kind of see this kind of work. And I just want a practical question. So imagine, I wonder how much it matters. So in healthcare, we often have many more and more covariance in the data, right? So
yes.
Even with presumably large sample size, we now control for so many things in their interactions that actually many cells are small.
Yes.
And I wonder to what extent the imbalance of smallness. So you can imagine everything is pretty large, but there's one racial category, whatever, or something that is kind of, so this kind of local small sample is just like one thing, and then I can imagine uniformly splitting to many small cells. So
yes.
Yeah.
So this is a point made by Dan Moore et al. In I think 2021. I'm never sure how much to play it up, but the argument that they're going to make is basically, as we go to a big data world and we have a bunch of covariates, it might be that we have most of our sample that we can, there's really overlap, but kind of inevitably we're going to have some regions that we can predict treatment well, meaning we should expect weak overlap to be more and more of an issue. So a couple of notes. So one is this gamma parameter is important for how things are going to work. So if you're in a situation where you have a few small regions where we can predict really well, but as a matter of the population, it's 0.1%, 0.01%, kind of intuitively that population isn't going to make much of a difference. What my results are going to say is basically as long as you do something to try to capture that population, you're going to be fine. Where we really have an issue is if it's not just a few people we can predict well, but kind of the covariates are allowing to predict a lot of people well. That's going to mean we have a gamma that's smaller, we have more small propensity scores, and that's going to mean that we really need to do something a little more sophisticated to target the full population. So that's point one. And then point two is you mentioned the phrase strata. So there's this great work by Peng Ding and others that say if you're specifically thinking about a strata stabilized estimator, then this issue is actually not so bad. So right, what's the idea? So if it's not just, we have continuous covariates, but everyone is in a discrete cell, then, if we have cells that have small treatment probabilities, we'll have a cell that has, weak overlap, we'll have mostly control units, but as long as in the cell with the fewest treated observations, the number of treated observations is going to infinity, then we can do our asymptotics in that cell, and we're going to get a central limit theorem at a slower rate. So actually, if you're doing something stabilized, you actually don't need all of this work. What you're doing, it turns out, is going to already work. This is what to do in the case where in the limit our cells or our sizes are going to 0, meaning we can't just think we have a cell that's going to infinity slowly.
Okay, so maybe this is more of like an estimation question, and not an inference one. But when I see like the clipping area, that seems to tell me like, okay, this is a region where the p-scores are huge or tiny, and that's sort of special for the p-score reason.
Yes.
But those are maybe also regions where I want to like rely more on the outcome regression part of the or the double beer bust estimator. So should we be thinking about the B region of propensity scores as also a place where we should be flexible or special in some sense in our like outcome model, you know, like put an interaction in there, put a kink in there or something.
Yeah, so
You can mark those observations because you have the propensity score, you can just mark them.
You're like, for this subset, I'm gonna do the B thing.
yeah, exactly. So there's, I should say that there's papers that do smarter things about what you can do in those regions. So the analysis that I'm trying to do is kind of, what if we want to do something really dumb? You know, how can we get things to work? I mean, maybe not really, really dumb, but like we're not really being that sophisticated. So for example, Ma and Wong are going to have a much more thoughtful debiasing. Yulong Wong, Sasaki and Ura have a really thoughtful debiasing with Pedro Santana and others. So you really should think about it. In the background, I should say the estimator that I'm doing here when we do regression. Say it again.
No, it's not doubly robust.
So it's going to go into something doubly robust where you estimate an outcome, mean, and a propensity score. But the outcome model here, I'm being more sophisticated to deal with weak overlap. Because exactly this, so if you do local polynomials, so think kernel regression, you know, you have this region where you have fewer observations, which means that you kind of need to increase your bandwidth, right? You're going to have too much variance with the usual bandwidth, so you need to increase your bandwidth, bring in more observations further away, which increases your bias. So you end up with a slower rate. So you should be thoughtful with what you're doing. In the simulations, I'm not being thoughtful because the philosophy of this paper is really like, how can we get things to work without having to be super thoughtful? But agreed, you can get more bite out of being more thoughtful and doing something smarter. Yeah.
I think, and I was thinking about like, if you have a propensity score, you can match those observations that you're clipping, and that's going to be important because, and going back to the discussion, because sometimes it's scale. Some of these propensity scores estimates are like very like if the scale of some of your covariates is really big, it just might push you. And really, that's not something to worry. Maybe you scale your data, like measure things in thousands or something like that. Now, if there's something along the line where like these people are like never going, these are people like you should take a surgery or something, but you can observe this in your covariates sometimes.
Yes.
So being able to mark is I think important. And it's already an input. It's more of a cosmetic thing when you do, and like it's software design, I guess. And then the other comment I have is there's some literature about normalizing estimators for like propensity scores and all this kind of this whole literature. There's a really nice paper of like data Lewis out, Jeff Woodridge, and Simon Slosinski, where they do actually in a different context. But they characterize what happens when you normalize and not normalize in different scenarios. And they do it in the context of local average treatment effects, but it's kind of nice because it tells you a little bit about, okay, what are the benefits of normalizing. I think that's a really nice kind of idea of doing it, and the cost of it is not.
Really good comments, appreciated. My favorite example of the first one is if you have a logit model and you have one covariate that's unbounded and the coefficient on that covariate is not 0, then your model is implying that as the covariate goes to infinity, the propensity score goes to 0 and 1. So like mechanically, we're introducing weak overlap in a sense in that case, and even if it doesn't really exist. So
and
I
the researchers
agree.
can look at it. Just look. Okay, these observations mean something to me or not. If it's
Great. Yes. Yeah, and to be clear, I don't mean this paper to say that the average treatment effect is the only thing of interest. But I think even if you kind of think that what we care about is maybe the population between 10% and 90%, I think still you want to know, like, is that the dropping of the remaining population driving your effects? So for example, the empirical application is right heart catheterization. The version of Andreas was kind of downplaying it, but now I'm making it a little more provocative. So this is the Crump et al. Paper that proposes the 10% rule. This is their empirical application. It turns out what they're doing is they're throwing out about 18% of the sample. Turns out that the treatment effect in the weak overlap region is pretty close to the remaining region, but that's not obvious. And you can certainly imagine other examples where throwing out 18% of your data, the data that the doctors think are people who don't need this treatment, flips you from a negative to a positive treatment effect, average treatment effect. And so at a minimum, we should know that. If we care about the subsample, the subpopulation, that's fine. But like we should know that that's driving our effects.
Thank you, Jacob. Thank you, Andreas. Tell us about principal components.